My pleasure to introduce John here, the Global VP of Technical Marketing and Business Development. My Patcham is now CZ headquartered in the UAE, US. Patcham is a global manufacturer with specialty additives for paint, coatings, paints, and plastic industries. Patcham manufactures, markets, and sells its specialty additives globally with staff and distribution network. Prior to his affiliation with Patcham, John was a technical product manager, paint additives division, and business development manager, paper coating additives of a dominant global specialty additive supplier. From that, he spent many years accumulating his collective experiences in research, product development, and technical service. Complement companies worked all in Williams. We finish general industrial aluminum extrusion, as well as a formulation of pigment concentrates for various market applications. He has held memberships and was an active supporter of Cleveland, LA, Southern New York, Pacific Northwest, Pittsburgh, and past president of the New York Society of Coatings Technology. He has presented numerous papers at technical conferences and podcasts during his career in the coatings industry. John's expertise is in formulation, interfacial chemistry, and resolution of coating problems. John received a Bachelor's of Science in Chemistry from Westminster College and his MBE from the University of Pittsburgh. Welcome, John.
Thank you. I'm going to take advantage of the height this podium gives me. I am greatly challenged. Thank you for attending this conference. What's the role of the HSD high-speed dissolvent in the dispersion system?
It's advancing on the screen. Oh, let me catch you up. Hold tight. Yeah, all right. I think we've.
The dispersion process. Okay, so we take pigment particulates, put the intermediate liquid, and these pigments come as glomerulates or fluxes. Put energy in using dispersion of some form. Break these particles into particle size so that they have deflocculated. Now, the only difference between flocculated pigment and flocks that we purchase are that these flocks contain air space between them, like flocculated pigment is voids are filled with the That's the only difference. We use this energy, put in sufficient energy to separate those particulates, their individual sizes. And when we turn the stirrer off, it will revert back to its former state, which is the flocculated state. So to prevent that, we in the industry use wetting, dispersion stabilizing. Here we see the same example. Water, hydrophobic pigment. On the left-hand side, we use a wetting additive. On the right-hand side, we use a high-performance waterborne additive that does not contain wetting agent for greater water resistance. And you can see that these materials added to the water render the hydrophobic pigment easily absorbed into the continuous space. That's the role of a wetting agent. Now, what's the role of the dispersion or dispersion stabilizer? To these 2 liters of water, we're going to add red oxide. Same amount, 65% per liter. One contains only water, the other contains water with some dispersion, 1%. And with this modest amount of dispersion force put in, we can see a significant difference in what behavior The left-hand side, you see without dispersant, it's very puffy, non-flowable material. On the right-hand side, you can see that it's more fluid, even with that modest amount of shear energy. So we see the function of wetting agent, dispersing agent. What are they actually, and what do they do? Well, the wetting agent lowers the surface tension of water so that it can be compatible with the hydrophobic surface, especially those organic fluids. So it allows it to be brought into intimate contact with our water phase. The dispersants, on the other hand, are used to coat the individual pigment particles so that when there is shear applied, those individual pigment particles do not impact each other. And by coating those pigment particles to eliminate that particle-particle contact, there is when we observe a lower viscosity behavior. So wetting agents allow it to be brought into the phase, water phase, dispersants prevent that particle-particle contact. Now, I say dispersants typically include dispersion stabilizing agents. They prevent the flocculation that will occur. Schematically, what we do is take those agglomerates and flocculants, subject them to shear, that separates the individual pigment particles. Hopefully, the dispersion stabilizing agent to prevent the flocculation forces inevitably there. And we test these, we challenge physical chemistry. Population is going to happen regardless. So what we do, we put in conditions that will actually accelerate this one, elevate the temperature, put it under gravitational forces to monitor whether these are resistant to flocculation. In our typical industry test, is 4 weeks at 120 degrees hot or 50 degrees C to try and accelerate this. And then and only then, if it passes this particular test, there's no sign of settling, flocculation, or change of color, then we render it say as, oh, this is a good dispersant. So first, let's establish some terms that we're going to use for this presentation. Homogeneous, mixing of two liquids together. Emulsifying, mixing a liquid with an immiscible liquid. Then disperse, which is an incorporation of a solid into the. So under the terms of those definitions, we're going to talk about the HSD and dispersion process. You can see in this particular chart, the dissolver is used to reduce large particles down to a smaller size. Typically, depending on the binding media that you select, to down to 10 nanometers or less. Now, the functioning of HSD depends on the tip speed. I've walked through a lot of new manufacturing plants. Some of the things that I've observed are unspeakable, unforgivable. Something like with no teeth. Upside down. I've seen high-speed mixers not even in the liquid turned on with the assumption as mixing them. Well, these are parameters that we kind of assume are mixed. But sometimes they are not because we assume that the operator is trained. Those have housing. I have never seen an operator lift his tank so that the liquid can reach the stern. You will allow it to have infinite amount of power that you can put it. And batch operator only has on and off. And you can't pick up the tank. Doesn't move. So if you're picking up your container in the laboratory, in order to get that nice premix that you're supposed to see, it ain't happening in the plant. Now, You know that tip speed depends on the size of the blade. The bigger the blade, the faster the tip will go, given at the same RPM. And of course, we can calculate our laboratory tip speed and compare it to the production tip speed. And I have yet to see the manufacturing tip speed match laboratories. Not possible. The diagram, my table system. Notice that tank is only about half. That blade is down to 1/3 of the depth of the container. And then it's perfect. How close is it to manufacturing? How close is it actually to anybody's laboratory? We pick up that can, move it around until we get that nice color shape, kind of flip it. You can't move that production tank. And all the shear turn occurs at the edge of that blade, right at the tip. So this is what a good optimal formula for that premix looks like. Under that particular RPM and diameter blade. Non-optimal looks similar, but you don't get that vertical flow, the donut shape. So you're not getting the full dispersion, and the shear is not very. Edge like this one. Sometimes it's not good. All kinds of reasons for that. The viscosity is too low. The impeller is too deep into the system. Put way too much material into the container. But manufacturing isn't made to optimum fill. They usually like to use 90% more X volume. So you'll see this quite often in manufacturing, where you get, according to the formula, it's perfect, but there's just too much material for that particular blade diameter. And this is the recording. If you run your HSD constant speed as the mixture heats up, and I don't know if you're aware, that premix is supposed to heat. It should go from room temperature to about 120 degrees. It should not get much higher. If it gets higher than that, you need to reduce the viscosity of your premix. And so let's look at new manufacturing. I can just operate until summer and winter. So the premix is not getting hot, it's not thick enough. And if the premix is getting too hot, you need to reduce viscosity. And that's how you control the temperature, the amount of shear that's put into the system and the HSD. Because if it doesn't heat up, you're not putting your energy in sufficiently. And if it's heating too high, it's overheating. These are all measurable parameters that are available to you depending on your laboratory's supplier of the high-speed mixer. You also like to monitor what happens if you use a constant mechanical power. So as the energy goes up, of course, the RPMs can, and you maintain a constant power. Other side, a giant impeller takes up 90% diameter. That's why typically ideal diameter is 3 times bigger than the diameter or other subverts into the depth. And there are various ways that you can optimize your buildings. Every building is for its person. HSD preparation movies, and the suitable to feed into small media building uh, building system. So how long you disperse it? Get the Dunham effect, shaft speed. How many square feet? The amount that you put in the middle base, the amount of filler, pigment concentration, hyperflocculation, deflocculation, you're looking for your eyes, and also specifically volatility. HSD works from shear, high shear. Works on liquid used with large amount. Typically, this is used by determining dangerous flow point, minimal dispersal in solvents with a combined mixture and flow. And optimal dissolvent dispersion may do most of the work making dispersion. In architectural, there are many paint companies that actually use only the HSD to generate their finished quality paint. But for those particular applications, that degree of dispersion is acceptable. They know they can not getting the best dispersion, but for their process, it result in the most efficient way. However, for higher quality coatings, you need to eliminate the small distribution, larger pigment particle globulars. And this is where the HSD is used to reduce those pigment particles to a size. So let's look at why would you use a beam for a dissolver? Well, the dissolver works best at reducing the largest particles down to a smaller size. Beam you can put in much higher energy to decide on the max brightening behavior that you use. You can further de-agglomerate all those agglomerated pigment particles, and it's actually capable of breaking down the primary particle sizes. This is where today, when you have these new organic pigment particles, when you're dispersing them, you're actually reducing that primary particle size to smaller than its primary particle size, and that introduces a whole different set of optics to the pigmented system. I think people have had the experience of a batch of mill base that does not exhibit a good pigment grind, but shows good texture, great color. I see it here, yes. I've seen it too. So what's the typical solution? Try and filter it out. It's a little too small to be filtered out. Can't quite get it out. So you try milling it some more. Mill it, and it still gives a bad pigment, right? Interesting thing about pigment, who knows the origin of pigment? What industry started? You don't know, it was the chocolate industry. Your tongue was capable of detecting 4 nanometers particle size. So it was used as a judge whether the chocolate was smooth or seedy. Well, we use it in the paint industry not to see how good your brain is, just to see how bad your brain is. It tells you the largest particles that you have in your brain. Your taste strength tells you the small particles and its color. Now, the reason why more grinding does not remove those particles and does not increase the paint strength is because the amount of pigment particles that are giving you this bad pigment grinding are very, very small percentage of the total color. You have the total color, but you not have the dirty grind. And why you have a dirty grind is because of the nature of small media building. You can see using these two diagrams as examples. Those large particles from the left-hand side. The orbit of one tip actually smaller medium particles. So the purpose of HSD is the particles that particle is now small enough to pass through the shear zone and binding media. I envision as if your binding media is the size of basketballs. If your premix is feeding it particles the size of volleyballs, those pieces of pigment act like grinding media, circle around, because they're almost as big as the grinding media. You have to feed your ping pong size particles as the media so that they can be subjected to the shear zone. So various parameters that impact bead number. Of course, bead size. We're moving to finer and finer bead size. What's that mean? We're going to have better HSD. You can change the parameter so that there's a great difference because that's where the image is here. Loading of beads, surface area that's related to the size of the beads, how fast you turn the system, what's the residence time, is the magic temperature. If you increase one bead, especially if the system starts to open, there are many pigments that are temperature sensitive, change the color of your pigment, and not able to control it. How long it's in the mill, and specific formulation. What do you need the stabilizing additive chemistry that you use? That is dependent on the formulation and totally dependent on the ability, the binder, solubility of the liquid system. Last thing you have to experience and then type of bead. You make different types of bead available to you. And remember, each formulation is designed specifically for a specific build and grinding bead. Change one of those parameters. For example, if you change the mill, you're not surprised that it won't work. It's a different mill. But many chemists are surprised that you change the grinding media, totally change the mill, because the media is a part of the mill. And the formulation of the mill base is dependent on that mill and the media that you use. The smaller your media, the more horsepower it is. Because it's more content area. So graphically, it's the whole summation of the talk. If you don't do a good premix, you're not going to get a good mill. Because those big particulates act as grinding medium, that is why when you regrind it, it's subjected to the same again. It's still a smaller piece of medium, and it just orbits or rotates in the system. You have to get it smaller so that it's exposed to shear range of the material that you use. So the dissolver is a very critical part of preparing that mill base for bead. Formulation of the mill base, very critical part. Understand the mechanical requirements for optimal. If you do something special, like hold your left leg up in the air, do a magic chin, you simply the pigment, something magic. That's what you do. You have all the information. appreciate the interdependence of every component in your formulation and the operational parameters. Better you do your premix, better the dispersion will be. Thank you. Okay, question?
So with technology, we're asking our questions through the app. I do have two that we have for you. If you have any additional questions, please ask them. And if you don't have the app, I'll walk over to you with the question. So the first one we have for you is, if the temperature gets too high through agitation, this negatively impact the dispersion performance.
It can. First of all, you lose solid. And especially if your pigment is temperature sensitive. Okay.
Second question I have here is, you indicated that you should use or reduce viscosity to control dispersion temp. Can you utilize the shaft speed RPMs?
You can to reduce the amount of shear put into the system. Remember, this is an interrelated system. Integral.
So to extend the time I do the
Well,
residence time?
not necessarily. Every piece of dispersion equipment is only capable of getting some finite number of energy into the system. You can lower the energy, increase the time, but only reach a certain degree of dispersion. And it may not be the degree of dispersion that you're looking for. So if you have infinite time, you don't care about the number of hours. Theoretically, you can achieve best dispersion that you can at those RPMs. Allow the system to cool and then crank it back up. That's not an efficient way of operating. If you balance, you may adjust the formulation by reducing the pigment load. That will also lower the temperature. But typically, it's easier just to someone to. Another way is just to lower the pigment load so that the number of particulates in the shear zone are reduced. That can also reduce the temperature. And if you're lucky enough to have a cool high-speed mixing tank, it depends on how cold you're.
Makes me want to ask another question. So if you have almost
Well, you know, I came from the old school where you looked. If I was stuck, if the system appears to be good fitting biscuits, you have a couple options. You can add solvent to it. And if you add solvent to it, you see no change. It's still puffing. That tells you that it needs more dispersing or binding. So that matches. Daniel's low point, where the minimum amount of binding is used to take up the space between all these pigment particles without particle interaction. And yes, that will get you close to what the rational looking system is and how efficient the dispersants are. But typically, there's no replacement for the chemist's eye. Look at it, put it in high-speed mixture, look at it. It's just going to do. If it does, what happens if I add a little more pigment? You see a dramatic difference right off the working. Add some solvent to it, you see a difference in behavior. And with that, you can figure out this is the maximum pigment volume. I see some heads going up and up. It's good because you're looking at the system rather than blindly following a recipe. Right? Because, if we just follow a recipe and alter, we don't know if we have reached optimal conditions for that particular situation. And there are many chemists that are concerned that their premix starts turning, it gets hot. Hell, it's supposed to get hot. That tells you that the energy is going in. But if you only get this hot, you should be able to always touch the container. If it's too hot to touch, you better modify it because it's going to get a lot hotter than manufacturing.
And we have some more, so in a little time, so I'll continue. This color, the rotor state feel more effective than the Phyllis,
Many ways,
tell us.
there are many ways to introduce shear into your system. They all work to some extent. But the mill-based formulation has to be optimized for that specific mill system. And I can't overemphasize that. Many of us kind of make the assumption, well, it works in this mill, it should work in that mill. So let's compare the two and see which is more efficient. With that mill base, you change the mill base, you can really modify, try to optimize for each particular mill condition. And that's like saying, I'm going to make the best system I can with this particular resin. And I go tell my supervisor, this is the best way possible. I can always look at my mind. In a big formulation, there's so many interdependent conditions going on. Everything you do for one does not operate independently from all the rest. And just to add, it's possible to use high shear, very high mass grinding media on light yellow pigments. I actually did it. I took the light yellow pigment and made the mill by steel aluminum. I just pulled them. But it was faster to dry. Got the right color rate. It didn't change the color. It wasn't good long enough to be this color. So it all depends on the condition that you run a mill in. Because when I heard, oh, you can't do a light yellow steel shot. I can't. Residence time is going to be pretty low. Change the color.
Yes, we do. This is the right distance. I think my brain is still 18, but physically, my eyes are not 18. How is the shear range determined for different media? And how do you determine if particle media be appropriate for a given pigment?
That's a touchy one because the only answer I can give is it depends. The greater the difference between the mass of the grinding media and the density of the mill, the more energy it's going to put in the mill base. But the closer the dimensions of the specific parameters to are, you're going to see less of a shear zone as the media is stirred in the system. So it depends on the amount of shear you want to be able to generate with the speed that you're stirring it. Very much.
Okay, looks like I do have one final one. Also considering the time we have the session. The last question: are there pigments that are too hard to be broken up by HSD or milling? How much impact do those materials?
Well, remember, the HSD is preparation and premix for milling. So if you use the the smaller your grinding media, better your premix has to be, and then maybe possible to take your premix and go to multiple stages of milling with different size media. Because I've seen some very, very fine small media that you would have to mill first to prepare the millimeters for that particular size of media. So the question is, it all depends. I'm sure that given the right motivation, any chemist can make that formulation work. Depends on how much time and effort you put into it and what your yield expectation from that yield is. You only get 10% yield. I doubt if your supervisor will find it acceptable.
Very good questions from the audience. Very